Scientists don't know why a comet that is located just past Jupiter has been erupting at random for years. Furthermore, they are not insignificant flashes. It is actually regarded as the solar system's most active comet. It has erupted 4 times in 2 days without warning, brightened almost 300 times in a matter of hours, and launched more than 1 million tons of debris into space faster than sound. Even more bizarre is the fact that these explosions have no apparent cause. It is merely an icy rock acting in ways we have never seen before. It does not swing violently toward the sun. Today, we'll explore what we know about Centaur 29P, including the reasons behind its erratic behavior and the latest discoveries made by the James Webb Telescope, which occasionally contradict our preconceived notions. While comparing images of the night sky at Hamburg Observatory in 1927, 2 astronomers named Arnold Schwassmann and Arno Arthur Wachmann made the discovery of Centaur 29P. It was initially believed to be a short-period comet, but it was later reclassified as a centaur, a kind of object that orbits the Sun between Jupiter and Neptune and possesses characteristics of both comets and asteroids, much like the mythological centaurs were half horse and half human. Centaurs most likely originated in the Kuiper Belt, but over millions of years, the gravity of the gas giants caused them to move inward. Their orbits are typically erratic and unstable. The majority will either be expelled entirely from the solar system or plummet into the inner solar system to become comets of the Jupiter family. They are therefore a transitory group with a brief lifespan. When Jupiter's gravity changes its orbit around 2038, Centaur 29P may potentially be propelled closer to the Sun. However, 29P stands apart in 2 significant ways. First, unlike other centaurs, its orbit is nearly a perfect circle rather than stretched out. Secondly, it's enormous. It is one of the largest comet-like things in the solar system, measuring 60 kilometers wide and larger than 96% of all known centaurs. Naturally, it then explodes a lot. With over 30 outbursts annually, 40% of which are totally unpredictable, it is the second most active body in the solar system after Io. The comet experiences abrupt and severe fluctuations during its eruption, peaking in brightness in 2 to 3 hours. When it erupted 4 times in 2 days in 2024 and shone about 300 times brighter than usual, it attracted news. Centaur 29P launched more than 1 million tons of debris into orbit 2 years prior, at velocities faster than sound, akin to popping the cork from the solar system's most pressurized champagne bottle. 5 and 7 days after that enormous eruption, there were 2 lesser explosions, which appears to be a common pattern for this comet. And it becomes even more bizarre just when you think that's extreme. In September 2021, Centaur 29P put on the most dramatic show in 40 years, erupting 5 times in a row. Surprisingly, it wasn't professional astronomers who first noticed, it was amateur stargazers. This is one of the many quirks of 29P's history. Most of its eruptions are initially spotted by hobbyists. After all, it's much easier to point a backyard telescope at a randomly exploding comet than to secure time on a multi-million-dollar publicly funded instrument. When scientists finally got word, they scrambled to get precious Hubble observation time. But the universe had other plans. A technical glitch forced Hubble out of commission the day before the observation. So what's behind these explosive episodes? You might guess volcanoes, and you'd be partly right, but these aren't the fiery lava-spewing kind. They're ice volcanoes. Centaur 29P is a cryovolcanic comet. Its surface is an icy shell, while beneath it lies a mix of ice, dust, and frozen gases like carbon dioxide, carbon monoxide, and nitrogen. Over time, radiation weakens the crust, slowly turning solid ice into gas. This builds pressure inside the comet until the shell cracks, unleashing a powerful eruption of cryomagma, a mix of frozen water, ammonia, salts, and volatile gases like methane and nitrogen. Basically, a volcano made of ice. Because 29P has strong gravity, most of this material doesn't escape into space. It falls back, rebuilding the crust and sometimes triggering follow-up eruptions a few days later, like those seen in 2021. The dust and ice form a hazy, reflective cloud around the nucleus that can linger for days or even weeks, making the comet appear far brighter, sometimes by hundreds of times. Some cryovolcanic comets, like 12P, nicknamed the Devil Comet for the horn-like plumes that appear during eruptions, have elongated orbits, which makes them more active when they get closer to the sun. Centaur 29P, however, moves in a nearly perfect circle, keeping it at roughly the same distance from the sun. You might expect this to create steady, predictable behavior, but 29P has other plans. Why are its eruptions so unpredictable? Scientists have long puzzled over the pattern of 29P's outbursts. Some suspect its unusually slow rotation, 57 days, plays a role. Observations show that major outbursts often occur every 52 to 60 days, while smaller eruptions can happen every 30 or 90 days. This suggests there might be some hidden seasonal cycle governing the comet's chaotic behavior. Even though Centaur 29P's eruptions seem to follow a rough schedule, their exact timing and strength are completely unpredictable. That hasn't stopped scientists from trying to guess when this feisty little comet might blow its top. In April 2023, scientists noticed something unusual. The light around the nucleus had dimmed more than ever, hinting that outgassing had slowed down. They realized this meant pressure was quietly building inside the comet, making an eruption almost inevitable. And sure enough, later that very same day, Centaur 29P gave off a mini outburst. For the first time, astronomers weren't just reacting to chaos, they had predicted it. It felt like a breakthrough, and with the James Webb Space Telescope, another surprise was waiting.
Until recently, carbon dioxide had never been detected on Centaur 29P. Astronomers had assumed carbon monoxide was the main driver of its eruptions because it's always been found in large amounts around the comet. But in 2024, Webb's data changed the picture. Earlier radio observations showed a single carbon monoxide jet pointing toward Earth, but Webb's near-infrared spectrograph revealed not one, but two jets, one aimed at Earth and one toward the north. Even more surprising, Webb detected two jets of carbon dioxide shooting from the north and south for the first time. The difference in the amounts of carbon monoxide and carbon dioxide suggests that Centaur 29P might not be a single body at all. It could be several objects clumped together. The exact reason for the outgassing is still a mystery, but there's an intriguing theory about the unusually high levels of carbon monoxide. This gas is extremely volatile, and pure carbon monoxide ice can evaporate at temperatures as low as 25 Kelvin. If it were sitting near the surface, it would have all escaped long ago, so it must be trapped deep inside the comet somehow. One possible explanation is amorphous water ice. Unlike the structured, orderly crystals we're familiar with on Earth, amorphous ice has a loose, irregular structure that can trap gases inside. When it warms above 77 Kelvin, amorphous ice gradually transforms into crystalline ice, releasing the trapped gases in the process. So if Centaur 29P still has amorphous ice in its interior with carbon monoxide trapped inside, and that ice is slowly turning crystalline, it could explain the unusually high levels of carbon monoxide escaping from the comet. In other words, the comet's interior might be a frozen pressure cooker, quietly storing energy and gases until the moment it explodes. So how solid is this theory? Let's break it down. Centaur 29P began its journey in the Kuiper Belt, where temperatures hover between 30 and 40 Kelvin. At such frigid levels, all ice is amorphous, basically disorganized and capable of trapping gases. Ice only starts crystallizing when it warms above 77 Kelvin. Over the course of 10 million years, as Centaur 29P drifted inward to its current orbit about 6 astronomical units from the Sun, temperatures rose to roughly 115 Kelvin. This triggered the slow conversion of amorphous ice into crystalline ice. But here's the big question. How long will it take for all the amorphous ice to change? Remember when we said 29P's size matters? This is exactly why. Researchers looked at smaller centaurs between 1 and 6 kilometers across, with similar orbits. For these tiny bodies, it would take between 0.1 and 6 million years for all their amorphous ice to crystallize. By the time they reach 6 AU from the Sun, they've already converted completely. All trapped gases are gone, leaving predictable, stable behavior.
Centaur 29P, however, is huge. Its 60-kilometer nucleus would take an estimated 60 to 100 million years to convert all its ice. If these numbers are right, it's likely only 50 to 65% of its amorphous ice has turned crystalline. That has huge consequences. As lower density amorphous ice shifts to denser crystalline ice, the nucleus shrinks slightly. This can create cracks, cave-ins, landslides, and even sinkholes, all of which could trigger the comet's unpredictable outbursts. But here's the kicker. Centaur 29P doesn't just leak gas slowly. It erupts violently, sometimes multiple times a year. How pressure builds quickly enough to trigger several back-to-back explosions is still a mystery. Why 29P suddenly brightens and the exact mechanics behind its eruptions remain two of the biggest questions for astronomers studying this extreme comet. It's a constant reminder that icy bodies in the outer solar system can be far more explosive than we once thought, and there's still so much we don't know. The good news? Progress is happening. Step by step, we're unraveling 29P's secrets. Instruments like the James Webb Space Telescope are opening doors to discoveries we could only dream of before. And the lesson goes beyond astronomy. Keep exploring, keep questioning, and never stop learning, whether it's about distant cryovolcanoes or the mysteries closer to home. Thanks for watching, and we'll see you next time.